All right, reversible reactions. Most chemical reactions that happen around us are reversible, which means the reaction can go in either direction. This is how we define things. The things on the left side of the arrows are the reactants. The things on the right side of the arrows are the products. We always designate those sides to be what they are. So when we're referring to them, we know which side we're talking about. But you're going to have a double arrow in here in between because it's showing that it's reversible. So A plus B are the reactants, C plus D would be the products over here. Now, when we're going from reactants to products, we call it the forward reaction. When we're going from the products towards the reactants, we call it the reverse. I know it says backward, but you could change it to reverse. We do call it the reverse reaction, okay? All reversible reactions have a tendency to reach a state of equilibrium in a closed system. We call this dynamic equilibrium. Don't write this whole thing down. Listen real quick and I will give you a shorter version to write down. Reaction said to be in dynamic equilibrium when the rate, this is about rate, at which the reactants are producing products equal the rate at which the products are producing reactants. So it is an equal rate situation. Rate of the forward equals the rate of the reverse. This is what you should write down. This is the important part. And realize that when we say dynamic equilibrium, that the molecules are in constant state of process. You have reactants making products, you have products making reactants. Keeps going back and forth. It's actually a very energetic situation going on. However, this is going on at the atomic level. We can't see that. What we see is a static view. We see the macroscopic view, and we can't see the dynamic processes happening all at once. Okay? So this is a dynamic process. It is a constant state of change, back and forth, back and forth, back and forth. But to us, because we only see the macroscopic view, it looks static. Okay? Now, learning check real quick. Let's see if you can figure this out. We already kind of discussed vapor pressure, but this is kind of what we're talking about here. Remember in my water bottle, I talked about this last time, that the water is evaporating, the inside here it's a closed container, and then the gas is condensing, and it forms that little layer of vapor pressure on top of the liquid. So keep that in mind when you're looking at your choices up here. Okay? Water molecules in a sealed jar are in a state of dynamic equilibrium because water molecules are A, condensing at the same rate that others are evaporating, B, are evaporating faster than they are condensing, C, cease to form when the air in the jar becomes saturated, or D, form only at high temperatures. So if we say dynamic equilibrium, what should we be constantly looking for? What keywords? We should be looking for rate, something about rate. Rate should be what? Equal. So we should be looking for something where it says equal rate, back and forth, back and forth. So what would be our best choice then? A is the best choice, definitely here, okay? So keep that in mind. Even though it's evaporating, condensing, which isn't a reaction, it is still a dynamic equilibrium process. And this is a very reasonable kind of SOL question you might see. All right, equilibrium expressions provide a quantitative representation of how far a reaction will proceed and where the equilibrium position is going to be. We use this expression, it's called the law of mass action, and it's always the products over the reactants. But there's an added extra little tidbit. You have to raise it to the power of the coefficient in the balanced reaction. So here are our products. So they go on top, and they're raised to the power of their coefficients in the balanced reaction. And then the reactants are on the bottom over here. They are going to be raised to the power of their coefficients. In this case, we're using J and K to represent those numbers. One other thing that you should note, and I think I went over this when we talked about acids and bases, but when you put brackets around a substance, like if I put brackets around CO2 like that, I'm actually telling you the concentration of CO2. So brackets mean concentration, and we measure concentration in molarity, which is big M, moles per liter. So when you see brackets around something, so like in acids and bases, you saw this a lot. The concentration of hydrogen or the concentration of hydroxide, brackets mean concentration. Now let me tell you some important information about K. KEQ is the equilibrium constant. It differs for every single reaction. The only thing that can change a K value too is changing the temperature. The reaction is going to get to this established ratio of products over reactants raised to their powers. And if you disturb the equilibrium, it will shift, keep going back and forth until it gets back to that exact ratio amount. Okay? And when we're talking about equilibrium where the rates are equal, that doesn't mean amounts of products and reactants are equal. And it hardly ever is a case where they are actually equal. Some reactions you have more products, some reactions you have more reactants. So when we say we have more products at equilibrium, we say the products are favored at equilibrium, and that's where the equilibrium position lies. If we have more reactants at equilibrium, then we say the reactants are favored at the equilibrium position. Okay? So now we're going to practice writing out an expression. So let me show you how to do this one. You are still going to, follow what we just did. Take your products, okay? You're going to put those ones in the numerator on top. Our first product is CO2. I'm going to use a different color. I don't like it. Here, we're going to use CO2, okay? And we're going to raise it to the power of the coefficient, which happens to be a 3. So it gets raised to the third power. Then water is our other one over here. So we put water on the top, the concentration of water raised to its power of its coefficient, which happens to be a 4. That's going to go in the numerator. The products always go in the numerator. Now for the denominator. Our first one is propane here. So we're going to put C3H8. The concentration of propane goes on the bottom. Its coefficient is an understood 1. Do we have to put a 1 though for a power? No, because it's understood, so we wouldn't have to include that. Here we're going to put O2, which is the other reactant, a concentration of oxygen, but it does have a coefficient and it's 5, so we're going to raise this one to the 5th power. So this is what I would write if I was writing out an equilibrium expression. Equilibrium expression. Okay? As you can see there, it is in type as well. Now, one little glitch to the fun equilibrium expression writing, which isn't very hard if you just memorize the pattern. You do not include liquids or liquids or solids. Liquids or solids are kept out of equilibrium. Pure liquids, pure solids, they are pure substances, and pure substances don't have changes in concentration. You remove some of the particles, you remove some of the volume, then you still have the same amount in terms of concentration and the particles per space, okay? So the only thing you would include in an equilibrium expression is going to be aqueous and gases. So anything that's AQ and anything that has a G next to it gets included. Anything with an S or an L, you exclude from the equilibrium expression. So if we were writing an equilibrium constant expression for ammonia reacting with water, giving you ammonium ion aqueous and hydroxide ion aqueous, which one would we not include? The water, it has an L next to it, we're not going to include it. It's not going to affect the equilibrium position because its concentration is not going to change. We leave it out. So the only ones we do include, now once again, these are products, so they go in the numerator. They don't have, they have 1 mole, so then they are raised to the first power, which you don't include. And ammonia over here. That one is also raised to 1 mole, and it goes on the bottom because it's a reactant. Does that make sense? Yes, okay. So now that we've written out the expressions, just like in math when you write out expressions when they give you variables, the next step is that actually give you concentrations, and so you can calculate the value. So let's do a couple problems with that. Before we get there, hold on, let's talk about what the K value will mean once we calculate it. K is greater than 1. That means that the reaction favors product formation. And you're going to have, oh, typo still there, more products than reactants at equilibrium. So if K is greater than 1, when you calculate it, you know you have more products. The equilibrium position lies on the product side, and products are favored. So you have more products than you do reactants. However, KEQ or K is less than 1, the reaction favors the reactants. More reactants than products at equilibrium. But let's think about this numerically too. K in general is the products over the reactants, right? Yes, you raise it to the power of the coefficient and all that good stuff. But if we have more products, the numerator is a larger number, right? So when you calculate it, you divide by a smaller number, you're going to get a number bigger than 1. If you have more reactants, though, than products, this number on the bottom will be larger. So you're going to get a number that is less than 1. Does that make sense? In general, how a fraction works, if the top number is bigger, you get a number greater than 1. If the bottom number is bigger, you're going to get a number less than 1. Correct? In terms of math, if you're thinking about it mathematically. Okay? So let's take this one into account, and the first thing you should do before you try to plug anything is write out the equilibrium expression. So over here you should start KEQ. Here is our products, so I'm going to put them on top. Concentration of nitrogen monoxide. We're going to raise that to the second power because it has a 2. And then on the bottom, the nitrogen dioxide goes on the bottom, raised to the second power. Once you have your expression, now you can just insert the concentrations where they're supposed to go. So, KEQ, here is NO, which is 0.160. We square that number times our oxygen, 0.080, over 1.20 squared. We're going to get our calculated value for K. And what does that come out to be? Anyone? And how many significant figures should we keep? That's a good question too. 2, very good. This value over here only has 2 in its measured value. So let's keep 2. Anybody calculate it yet? You can use the squared buttons on those calculators too, and that will be helpful and make it more efficient. Anyone? Anyone? Let's see what you get. Yes, do you have it? What's our value? 0.0014 is correct. In our calculators too, you might see it as 1.4 times 10 to the minus 3. Either or is fine. K values do not have a unit that goes with it. We don't put a unit on it. So in this case, K is what? Greater than, no, K is less than 1, right? K is less than 1. So what does that tell you about the equilibrium position? It is on the reactant side. Reactants are favored. Very good. Now try the next one real quick. Okay. Next one. If you wrote out the expression correctly. Up here, guys. Let's focus. We get SO3 squared over SO2 squared and oxygen. Okay, the concentration of oxygen. When you plug everything in, you get 0.78 squared over 0.44 squared and times 0.22. What is your KEQ? 14, good, 2 significant figures. K is greater than 1. Therefore, products are favored. The equilibrium position lies on the product side. Okay? That means you have more product at equilibrium than you do reactant, although they are still making each other at the same rate. Okay? Now let's talk about my favorite French guy. That would be Le Chatelier. We want to talk about Le Chatelier. All right, if a stress is applied to a system, the system proceeds in the direction that relieves the stress. Stress is any kind of change in a system at equilibrium that upsets the equilibrium. You can use Le Chatelier's principle to predict how the changes in concentration, that's one factor, the temperature or the pressure will affect an equilibrium system. So basically you stress it, it's going to proceed to a different side to relieve the stress until it gets back to its K ratio of products over reactants. So it's going to keep going, it's initially going to shift to one direction until it gets back, going back and forth until it gets back to its normal equilibrium position. The only one that will change the equilibrium position is temperature, but it still will have to alter the speed of the reaction in a certain direction in order to get back to relieving the stress that was applied for Le Chatelier's principle.